Welcome back, everyone, to, I guess, the new reality of how we're going to be doing Physics 2101 for a while. When we left off, we had just introduced the concept of potential energy, and I thought we would go back and revisit that introduction to get us started for today's lecture. So we introduced this concept with the idea of this problem where we're dropping a microphone from a height of 2 meters, and we asked the question: how much energy, how much kinetic energy does it generate as it falls from 2 meters above the ground to just the instant before it hits the ground? So if we start with, here's our microphone up here. So there it is. And it's at a height here of 2 meters above the ground. And initially it has no motion. It starts from rest, and so it has no kinetic energy to begin with. But as it falls, there is a gravitational force, mg, the weight of our microphone, and it's acting downward. And it acts through this distance of 2 meters, and so the work done by gravity as the microphone falls is the force of gravity times our change in altitude. The force is equal to minus mg, so it's in the negative direction. The displacement is minus 2 meters, and so the work done then will be minus 0.2 kilograms times 9.8 meters per second squared times minus 2 meters. So we take the calculator, 0.2 times 9.8 times 2, and the work done by gravity is 3.92 joules of energy, and that's got to be equal to the change in the kinetic energy. So that's the final kinetic energy minus the initial kinetic energy, and we said the initial kinetic energy was 0, so this is just equal to the final kinetic energy. It's 3.92 joules. So just the instant, here we draw it, there it's moving, just the instant before it hits the ground, it has this 3.92 joules of energy. Well, where did that energy come from? We just saw that the energy was work done on the falling microphone by the influence of gravity. But there's a definite difference between when we see the microphone up in the air and when we leave the microphone down on the ground. Down on the ground, we don't expect the microphone to have any motion no matter what we do with it, whereas when the microphone is hovering in the air, we know that as we drop it, then the microphone will spontaneously leap into motion, that's going to be the natural behavior of the microphone, whereas the natural behavior of the microphone on the ground would be to not move. And so, in a very real sense, sitting up here, there's more potential for the microphone to do something interesting than there is on the ground. And that is because the microphone is sort of separated from the floor here, and when you're separated from the ground or the floor you're in the context of a gravitational attraction to the Earth, then there is some potential for interesting things to happen as you fall. So we could think about this work done by this force as being a different kind of energy associated with the microphone. We could say that the microphone still has energy when it's up here in the air. Indeed, it has the potential to generate 3.92 joules of energy. And so up here, the microphone could be said to have, in fact, that same 3.92 joules of energy. It's just in a form of stored as distance from the ground. And indeed, in lifting the microphone up to 2 meters above the ground, you would have to do the same 3.92 joules of work to lift the microphone up to the ground. Remember, we did the problem with the weightlifter, and we asked, how much work did the weightlifter do lifting the weights? And then we found that the weights didn't have any more motion at the top than they did at the bottom, so we were doing work on the weights by lifting them, but that energy was being stolen because gravity was doing negative work in the opposite direction. Well, instead of thinking about the work done by gravity, if we thought about, well, we lifted the weight up and it didn't change the kinetic energy of the weight, but it changed the potential energy of the weight, then the work was still adding energy to the system as we lifted the weight or the microphone, but the energy wasn't going into motion or kinetic energy, but rather the energy was going into a change of position. So this concept of a potential energy then is an energy which is associated with these forces which are going to accelerate our object towards the ground, in the case of gravity, or other similar sorts of forces, where there's energy associated with a configuration or a set of positions of our system, right? There's energy associated with being above the ground in the case of a gravitational force, or in the case, for instance, for springs, there's energy associated with the stretching of springs or the compressing of springs. Because again, if you stretch a spring and let it go, we expect that the spring will snap back to its original position, and if we compress a spring and let it go, we expect that the spring will snap back to its original position as well. So these kinds of forces, gravity and Hooke's law, both of which are examples of a conservative force, and we'll come to a definition of conservative here in a bit, but these forces which are conservative can have a potential energy associated with them. And the definition of that potential energy, well, it's defined in an interesting sort of way. It's defined as the difference in potential energy. We don't actually define the 0 point of potential energy, but rather we define the difference between the potential energy as the minus the work that would be done by one of these conservative forces in moving from an initial to final position. So again, if we talked about the kinetic or the potential energy of the microphone or this pen suspended in air, that potential energy would be the opposite of the work done by gravity in getting it to that position from some other position. So if we start on the ground and we lift the pen up into the air, gravity's doing negative work because gravity's pointing downward and the motion is upward. And the opposite of that work up here would be the potential energy that the pen has up here. And then similarly, we could define it as a similar sort of thing. Here is this basically this integral of the work between initial and final positions, but here in multiple dimensions. Now, because we've defined the 0 point of potential energy, or we haven't defined the 0 point of potential energy, because we've defined potential energy as the difference between 2 points, then we're always free to decide where the 0 point for our potential energy system is. And typically there's a relatively obvious definition of 0 as the place where we don't expect interesting motion to spontaneously happen. So as I say, if you're on the ground, then you're done falling for the day. Which means that in the case of gravity, the obvious 0 point of potential energy would be wherever you're done moving or falling for the day. And we can see here in the example figure 3 different definitions of what might be the 0 point or the end of interesting motion, right? So for point A, where the book is above a table, probably you would define the 0 point of gravity or the 0 point of the potential energy to be on the table. If the book is on the table, it has no potential energy. Whereas at point B here, where the book is hovering above the floor, obviously the book is going to stop doing anything interesting when the book is on the floor. So the natural 0 point there would be to say that the floor is 0 potential energy. And at point C here, where we're hanging the book above outside the building altogether, again, the book is going to cease doing anything interesting if it's on the ground, and so you would probably define the ground as the 0 point in potential energy. It doesn't matter as long as you're consistent with how you've defined the 0 point everywhere in a problem. And you're free to choose whichever 0 point would be the most convenient. So again, if we're going to define potential energy as this difference in energy, or the which is minus the work done by a force between 2 points, then let's look at some examples of potential energy for particularly common forces that we would use potential energy for. So to begin with, let's talk about gravitational potential energy, or the force of gravity near the Earth's surface. And in this case, we typically again define the 0 point to be when the object is on the ground, or when it's on the table or the floor, or whatever the local place where it's going to stop moving is. So if we let the ground be the 0 point of gravitational potential energy, and we choose a coordinate system where we've set, for instance, the ground to be y equals 0, then the gravitational potential energy of an object above the ground would be m times g times y. So the weight of the object, mg, times its altitude, would give you the gravitational potential energy. The higher you are in the air, the more gravitational potential energy you have. Now, that works for the objects near the Earth's surface, where the gravitational acceleration is always this constant g, and therefore the gravitational force is always the constant mg. But it turns out that to explain things like the motion of the moon and the motion of the planets around the sun, Newton, in thinking about Galileo's version of the gravitational force, realized that he had to make a modification to Galileo's force law when there was a large amount of distance between the gravitating objects. And so Newton's version of the gravitational force law is a bit different and more complicated than Galileo's version. Newton's version of the gravitational force law is this one given here. There's this constant capital G, which has the value 6.67 times 10 to the minus 11. It's a very small number in the standard system of units. Newton meters squared per kilogram squared. So you have this constant, and it's the force is proportional to the mass of the two objects that are feeling an attraction to one another. So object 1 here might be the Earth, and object 2 here might be the Moon. And if you wanted to know what's the gravitational force of attraction between the Earth and the Moon, well, it's proportional to both the Earth's mass and the Moon's mass, and inversely proportional to the square of the distance between them. Now, this force law looks very, very different than F equals mg, the gravitational force law that we're used to seeing. But if we adopt as one of the masses the mass of the Earth, and the distance between the objects as the radius of the Earth, then it turns out that we can recover Galileo's force law. So if we take 6.67 times 10 to the minus 11 as the constant capital G, and multiply by the mass of the Earth, which is 5.97 times 10 to the 24 kilograms, divide by the square of the radius of the Earth, what you get is a constant that is 9.81 meters per second squared. So in other words, the gravitational acceleration constant, Galileo's gravitational acceleration constant, is in fact Newton's gravitational constant times the mass of the Earth divided by the square of the radius of the Earth. And then if you use Newton's gravitational law, you recover Galileo's gravitational law. So we can see that Galileo's version of gravity is a simplified version which works at the surface of the planet Earth, whereas Newton's gravity works also at the surface of the planet Earth, but also for all the other planets at all the other distances. Newton's gravitational law describes more of the universe, but it's also a little bit more complicated to use, and near the surface of the Earth you might as well just use again the old Galilean version. If we wanted to look at the potential energy that we would get from using Newton's gravitational law, then again we would define the change in the potential energy as the work done by this gravitational force. So we would plug in Newton's universal gravitation law here for the force law and do this integral. And if you do that, then you can derive a form here which depends as goes as 1 over r as opposed to 1 over r squared. And again, if we talk about changing from some initial radius r1 to some final radius r2, then the change in the potential energy would be written down as this difference in the 1 over r1 and 1 over r2. And the standard convention is to again ask, where is it that we could be around the Earth and have no expectation for motion? And the answer is, well, you would have to be infinitely far away from the Earth, before the gravitational force law wouldn't start you moving. And so if we define the 0 point of energy as infinitely far away from the Earth, then we can write down a unique form or a unique version of the potential energy, which is just minus g times the two masses and divided by the distance between those masses. Notice that the potential energy for Newton's gravitation law is always negative with this particular definition. One other force that we will use quite a bit to look at the gravitational force is the Hooke's law for springs, that says that the force is proportional to the displacement from whatever the equilibrium position of our spring is. And there's this force constant K. There is a spring constant. It describes how stiff the spring is. If K is a large number, newtons per meter, then that's a very stiff, rigid spring. If K is a small number in newtons per meter, then that's a pretty stretchy string. With this definition of force, again, we define the change in potential energy as this work integral between an initial and final position. And if we go ahead and do the calculus there, we can say that that change in potential energy is the difference between two terms, both of the form 1/2 kx squared. And by convention, again, the place where no interesting motion is going to happen spontaneously would be the equilibrium or unstretched position for the spring. So if we define that to be the place where potential energy is 0, then we can define the potential energy of a spring as just 1/2 kx squared. All right, so here let's try an example here with the spring force, and see if we can calculate this problem. So the problem says you have a force of 520 newtons, which is keeping a certain spring stretched a different distance of 0.2 meters. So if we have a force here, which is minus k delta x, that's Hooke's law, and it takes 520 newtons to get us a stretch of 0.2 meters, then if we take the magnitude of force here, then is 520 newtons. When delta x, our stretch, is 0.2 meters, then we can use that to solve for the spring constant K, right? So 520 newtons is equal to K times 0.2 meters, or our spring constant K is 520 newtons divided by 0.2 meters, which is 520 divided by 0.2, 2,600 newtons per meter. All right, so for each meter you would stretch this spring, you would the spring would generate 2,600 newtons of force. Well, what's the potential energy of the spring then when it's stretched to a distance of 2 meters? Well, we just said the spring potential energy, or elastic potential energy as it's sometimes called, so UE, the elastic potential energy, is 1/2 K, again our spring constant, times our stretch here, x squared. So in this case, that's going to be 1/2 our 2,600 newtons per meter, and 0.2 meters squared. So 0.2 squared times 2,600 divided by 2. Our elastic potential energy would be 52 joules. And if we compressed the spring by 5 centimeters, which would be a compression of 0.05 meters, right? Then our elastic potential energy in that case, again, 1/2 times our spring constant, 2,600 newtons per meter. And in this case, our compression here, it might be minus 0.05 meters squared, but notice that the minus sign doesn't really matter because we're squaring it anyway. So 0.05 squared times 2,600 divided by 2, that would be 3.25 joules of elastic potential energy. All right, so what's the advantage of talking about potential energy? Well, the advantage is that we can then, if the energies involved are all conservative forces, again, things like gravity or Hooke's law for springs, then an isolated system, a system which is not interacting with anything other than conservative forces, the total mechanical energy of that system will be conserved. We'll prove this in the next lecture, at least for a couple of different test cases. But for now, let's just investigate what this conservation of mechanical energy means and how we can use it to solve problems. What this means is that there's a total amount of energy, which is what you get when you add up the potential energy of all of the forces that are conservative forces acting on our system, and add it to any kinetic energy of that system. If that's conserved, then that means that this value for the total energy of the system will be the same number any way you add it up. You're just moving energy from one form to another. Here it might be all kinetic energy, maybe over there it's all potential energy, maybe somewhere in the middle it's a mixture of both of them. But the kinetic plus the potential energy will always add up to some constant value. And so we could write down an equation which says the total energy at the beginning of our experiment is the same as the total energy at the end of our experiment, or the total energy at moment 1 is the same as the total energy at moment 2. And then literally you just have to write down on one side of the equal sign the total energy at moment 1, and on the other side of the equal sign the total energy at moment 2. Another way that you could think of this is that the sum of the change of kinetic energy and the sum of the change of potential energy must add up to be 0. In other words, if the potential energy decreases, the kinetic energy must increase by that same amount. If the kinetic energy decreases, then the potential energy must increase by that same amount. These two statements are basically rewritings of the same thing. So let's go ahead and, again, try some problems and see what this would look like in practice. Let's put this to some work. All right, so it says a 2-kilogram block is pushed against a spring with a negligible mass and a force constant of 400 newtons per meter. All right, so we've got a constant here of 400 newtons per meter. We've got a mass here of 2 kilograms. And a compression distance to begin with, a delta x of some sort of 0.22 meters. That's probably going to come in and be useful for describing an elastic potential energy, it would look like. the block is pressed against this spring. So we have the block is squeezing a spring here like this. So we could imagine to begin with, here's a wall, here's some compressed spring. There is a compression distance here, which is our, oof, that pen's not doing so hot. Let's try a different one. All right, well that one's easier to see, but the purple may not be that different than the black is. There's our delta X from its uncompressed to its compressed position, and there is our block. When we release the block, it moves along a frictionless horizontal surface. So it moves this way for a while and then goes up a ramp, which is also frictionless. And there's an angle here of 37 degrees. And so the name of the game with these energy conservation problems, or to approach these problems from a conservation law standpoint in the first place, is to again identify the interesting moments in time, those being places where, or moments in the motion of our system, where we could say something about the states of energy. So one obvious position would be this first moment, moment one, when the spring is fully compressed and the box is in motion. And then we might think about a moment here, some moment two, after the spring has relaxed and the box has left the spring and it's just sliding horizontally along the surface, hasn't yet reached the ramp, but it isn't being accelerated by the spring. And then at some point it's going to start climbing the hill, and we could imagine here a third moment here when it's climbed the hill, and as it climbs the hill, gravity is slowly slowing it down, and there'll be a moment here, we'll call it moment 3, when the box briefly comes to rest. And so we've identified 3 interesting moments in time. The box isn't moving, but it's up against a compressed spring. The box isn't touching anything, it's in motion, and all of its energy would then be kinetic. And over here, the box has again stopped moving. It's not pushing against a spring, but it is now at some new altitude, some new height there above the ground. All right, so to approach this problem from an energy standpoint, what we would say is the energy at moment 1 equals the energy at moment 2, and it's equal to the energy at moment 3. The same amount of total mechanical energy would be present in each of these times. Well, what is the energy at moment 1? Well, the energy at moment 1 is all going to be, let's see, is there a spring being compressed or stretched? Yes, there absolutely is. So there is a 1/2 k delta x term there, delta x squared term there. That's the elastic or spring compression energy. Is there any kinetic energy? Nope, nothing is moving. Is there any gravitational potential energy? Nope, because the box is on the ground. All right, so the total energy, the total mechanical energy of our system is, in this case, at moment 1, stored as just the elastic potential energy. And the energy at moment 2, well, in that case, there is no spring or elastic potential energy. Nope. And there is no gravitational potential energy because, again, we're still on the ground. No spring is compressed, but there is some kinetic energy. Yes. So the energy at moment 2 is then just 1/2 mv squared. All right, so the speed at moment 2, and we might as well put a 2 there to remind us that that's the speed here at which we're moving at moment 2. At moment 3, there's no spring compression, so there's no elastic potential energy. The box isn't moving, our block isn't moving, so there's no kinetic energy, but there is gravitational potential energy, which is the mass of our box times gravity times the height, this height here, at which we reached our maximum height above the ground. Now, the problem is eventually going to ask us about how far up the ramp we got. So that would be some distance L up the ramp, and we'll have to worry about converting L and H, and there'll be some sort of a trig function here because there's a ramp, and we'll get to the geometry of that for a moment. But notice here that what we have is that the energy at moment 1, the energy at moment 2, and the energy at moment 3, those are all in different formats. Here it's elastic potential energy, here it is kinetic energy, and here it is gravitational potential energy. But since energy is conserved here, there's no friction involved, then the energy at moment 1 and the energy at moment 2 and the energy at moment 3 must all be the same. So what we can do then is equate them, right? So if we want to say, if we say E1 equals E2, well, E1 is 1/2 k delta x squared, and that E2 is 1/2 mv squared. So what do we know? Well, we know the spring constant k. We know the delta x here of compression. So we know everything on the left, and we know the mass on the right, and we're trying to find the speed. All right, so if we solve this for speed, then we'll have what we want. We can go ahead and cancel out the 1/2s on each side, divide the mass over. So k over m times delta x squared equals v squared, which would then say that our speed is the square root of k over m times our delta x. So we could plug in the square root of 400 newtons per meter over 2 kilograms times 0.22 meters is going to be our speed. So we take 400 divided by 2, take the square root of that, and multiply by 0.22, and we get that our speed here is 3.1 meters per second. Okay. And if we wanted to then ask how far up the block does it travel before it starts to slide down. All right, so that's going to be relating one of these energies at moment 1 or moment 2 to the energy at moment 3. So we could go ahead and say, for instance, that energy at moment 2 equals energy at moment 3. Energy at moment 2 is again 1/2 mv squared. Energy at moment 3 is mgh. And now we got to do something about this height because we want to find this out in terms of L. So let's go ahead and redraw our ramp here. This point here, that side is the height. And this length here, that's the L that we're looking for. The angle there is 37 degrees. So opposite over hypotenuse is the sine of 37 degrees is h over L. So L then would be h divided by the sine of 37 degrees. But in fact, what we want to do is actually solve this for h so that we can replace the h in there with the L. So h here is L times the sine of 37 degrees. And if we plug that in over here, 1/2 mv squared equals mg times L sine of 37 degrees. And we're solving here for L. The masses cancel in this case. So v squared over 2g sine of 37 degrees is our length L. And now we can go ahead and start plugging things in. Our V here is the answer it was over here. So that's 3.1 meters per second squared over twice 9.8 meters per second squared times the sine of 37 degrees. So we take the 3.1, square it, divide by 2, divide by 9.8, and divide by the sine of 37 degrees. And this is 0.82 meters is our length that it goes up the ramp. All right, so again, the strategy here for these energy problems, identify the interesting moments that the problem allows, or that you know something about the state of the energy, or that you can, you want to know something about the state of the energy. So in this case, we had the fully compressed moment, the moment where all of the energy was in kinetic energy, and the moment over here where all the energy was in gravitational potential energy. And indeed, in this case, each of our special moments corresponded to a place where all of the energy was in a single form. At moment 1, all of the energy was elastic potential energy. At moment 2, all of the energy was kinetic energy. At moment 3, all of the energy was potential energy. We'll see some examples next time where it doesn't quite split apart so cleanly, but it is still going to be the case that we always can write down energy 1 equals energy 2 equals energy 3, or whatever, and initial energy equals final energy, if all of the forces are conservative. We'll also look at cases where we have some non-conservative force at work and how to deal with those problems as well. So that's where we'll pick up from next time, doing some more examples here with working with total energy conservation, or cases where energy isn't conserved. Until then, I will see you next time.